Okay, we're going to be talking about slope error in this video. So basically we have a slope and what we're saying is that the slope is somehow incorrect. So for our purposes, we'll keep it simple, at least as we build the scaffolding in this. So we'll just say it was some sort of mathematical failure on our parts. We did our ordinary least squares regression wrong, so for whatever reason we end up with a wrong slope. So in this case I have 1x, which is a wrong slope because we are using the same data that we have been using before, which we know from previous videos. If you go back, it should be 1.3x. So that should be our actual slope. Now, a couple of things, again, I want to just emphasize on this. This is really more for scaffolding. There will be one element of this that I really want you to pay attention to, and it will carry forward into other videos, and that is how we mathematically recognize whether or not we have some sort of discrepancy in our slope. And so that is how we might recognize that our slope is in fact in error. Then moving along here, notice that I've got in this column a new column, x minus x bar. I didn't put the subscripts I just because I wanted to drive home the point that these are in fact values of x, not individual observations. Although moving forward, I will use the subscript I, and you can think about that as an index value rather than an individual observation, where this would be like index 1, index 2, index 3, index 4. So when you see a sum series, it's just recognizing that, yes, we have more than one value of x. We have 4 of them, and we need to sum them when we start dealing with that. Also, same with our error term. There's no indexing on the e that I have up here. Again, I'll be using the I, much the same with that. And then finally, this remains the same, where it's the expectation of y given some x value minus the line where if we input the same x value, our regression line will spit out a y value for us. And so the error is the difference between those two terms. Now, I want you to recall this idea of covariance. Specifically first just x and y. So that's the summation of xi minus x bar times yi minus y bar divided by n minus 1. We have something very similar here for the covariance of x and our error term. We are actually going to, it won't be the exact same formula though, and I'll explain why here in a second, but one thing I want to point out is for us to be confident in our slope value, we want this to equal 0. If it does not equal 0, that's definitely telling us we have a problem with our slope. That is to say that there is some sort of slope error. We have some sort of discrepancy with our slope. It's off of where it should be. So it either needs to be, the numerical value of it either needs to be higher or lower. That being said, the formula that we're going to use for this, I'm going to start with the numerator. It's going to look a little different. And again, you can think about the i's as indexes, not as individual observations. But notice I'm not putting ei minus e bar. There's a very particular reason for that. So if we have a good intercept, which I left 28.2, so we know that is the right intercept for this, then we could be safe in the knowledge that if the intercept is good, our summation of the EIs should equal 0. That is the summation of our error terms. And what would we say our mean is in this instance? Well, our mean is 1 over n times EI. And if EI equals 0, and this equals the mean, if we multiply anything by 0, we just get back 0. So that is to say that our E bar has to be equal to 0. So that eliminates our E bar for us. So really just more a mathematical underlying reasoning for why you won't see that here. And then if we come here we would say, okay, normally we divide by n minus 1. If our target equals 0, I want you to think about this for a second. Our target equals 0. You can never get 0 out of a denominator. If you divide by 0, it's undefined. So there is no way for a denominator to take us to 0. That means only the numerator can take us to 0, which makes our denominator in this instance irrelevant. You could also think about it in terms of our target as saying, okay, we could take the n minus 1 and just multiply it out into 0, and algebraically that makes it go away, if that's indeed our target. So a couple of ways in which we are reduced to this terminology when we say the covariance of x and e, where e is the error term, we just end up with the summation of xi minus x bar times ei. So hopefully you've found that useful. Now, these conditions are what I want you to remember. This is important. This is how we recognize whether or not we have this slope error. And this will extrapolate further as we move on through this course. That being said, what I'm going to show you here, because we're just assuming, for simplicity's sake again, that our ordinary least squares, we just made a mathematical error, some sort of mathematical mistake, and we ended up with a bad slope. If that is the case, and this is just straight out of a sample, we can return to a good slope with a mathematical correction that I'm going to show you here. But what I want to stress, or where I'm stuttering and where I'm going with this, is I don't want you to think, oh, then this mathematical correction, we can just use it when we start talking about the disturbance term. This will not apply in that case. So this will be what we're talking about from here on out will not carry forward in the same way, though, that the covariance of x and e, this concept of x covarying with some sort of error term, that will be retained as we move forward. So just wanted to make and draw that distinction. It'll start to make sense more too when we actually get into talking about the disturbance term, but for now I kind of just have to draw that distinction. So if we want to return, though, in this case, so in our simplified example here where we're just saying, oh, we just made some sort of regression error, then the way we'd return mathematically is there's this idea that our true slope coefficient will equal the slope coefficient that we calculated plus covariance of x and e divided by the variance of x. Now, the interesting thing again here is if this is correct, or if this slope is correct, this has to be 0, so that should be obvious. Then we're just left with, okay, beta 1 equals beta 1 star. That is, our slope equals the slope that we calculated for, the true slope equals the slope that we calculated for our regression. So now with that said, this formula breaks down into sigma xi minus x bar times ei. The e bar should be obvious why that stays away, because it equals 0 when we have our correct intercept. However, the n minus 1 goes away because variance of x also has an n minus 1 in it. So we've seen that before. If that feels unfamiliar to you, send something in the comments. I will send you a link to one of my previous videos where I do talk about that. So, that being said, we're left with this formula here. Xi minus x bar times ei all over the variance of x. That's how we repair it, is we take this, we're going to calculate this in this example, and we'll attach it here and then add it to what we have for our beta 1 star. We can go ahead and erase our beta 1 star. We know what we have right now is 1, and so what we need is this. The calculation have made it easy for us. And again, think of these x's, i's as just saying, oh, it's the index values. So it is going to be these values that I've already listed out. We have negative 1.5. We're going to multiply that by its associated error value, 3.8. Then we're going to add negative 0.5 multiplied by 3.8 for the same reason. Just run across the second row there. Then we'll have positive 0.5 multiplied by 3.8. These will cancel because we have both of them multiplied by 3.8. One is negative 0.5, one's positive. Those guys cancel. And then finally we have in our fourth row at the bottom here, 1.5 times 4.8. So these will sum to, this is going to be negative 5.7, and then we're adding 7.2 over here. Negative 5.7, 7.2. That's going to give us 1.5. So right away, again, we can reiterate, yes, we definitely have a problem when it comes to our slope. It is not equal 0, so alarm bells should be going off. And again, this is the step that you'd want to remember, is just being able to test it. That is the covariance portion of this equation. The rest of this repair, however, is just unique to this problem. But retain that we have 1.5. Now we need to calculate just the variance of x. And real quick, that's going to be, actually I'll just erase this so we got the room. So that's going to be negative 1.5 squared plus negative 0.5 squared plus 0.5 squared plus 1.5 squared. These will, I'll shorten this for you. You could check it on your own time with your calculator. They will sum up to 5. So that is, we're going to end up with 1.5, that was the covariance of x and its error term, over the variance of x, which is 5. So it's 1.5 over 5. That gives us 0.3. We insert that here. We end up with 1.3 back where we want it to be. So hopefully you found this video useful. If you did, like, comment, and subscribe. And I will see you guys next time for the disturbance term.